Okay, impulse, quite an interesting topic. Let's start with the basic definition word. So impulse is equal to change in momentum. Okay, so that's the first thing you have to understand. So the formula of the impulse is force times change in time. And change in momentum is final momentum minus initial momentum. Sometimes at the start it's written like change, delta P, which means PF minus PI. Right, so to understand what impulse is, take the example of a mass that's falling to the ground, and we'll look at two cases. Right, the first scenario is the mass falls to the ground and it reaches, a concrete ground, right, or concrete material. When it hits, we can imagine what will happen to the object. So just before it hits the ground, the mass will be moving at a certain velocity. Right, we can imagine that velocity is going to be quite fast. Right, so the initial velocity. So initial velocity is quite large, say large. Right. Again, we imagine the same mass falling to the ground. This is case 2. But this time, when it reaches the ground, right, it's not going to hit concrete, but you can imagine that the ground is made up of some softer material, maybe cardboard boxes. So just imagine a whole lot of cardboard boxes, or some sort of spongy material or springy type of material, right? Some soft material, right? So when it hits the ground, the impact will be quite less. Now, just before it hits the ground, of course, it's going to have the same sort of large, have the same large velocity before it hits the ground, because it's falling under gravity. Now, in the second case, now let's look at the first case first. The first case, when it hits the ground, it's going to come to a complete stop, right? So final velocity is going to be 0. Same in the second case, final velocity is going to be 0, right? When it hits the spongy material, the spongy material will slow it down, and it'll also bring it to a complete stop. In the first case, for it to come to a complete stop, the time it takes to come to a complete stop is going to be much, much less, right? So if we say that the time taken for it to come to complete stop is change in t, so this is going to be quite small, right? Of the two cases, in the first case, if the object was made of like wooden material or some sort of material, or fragile type of material, when it hits the ground, it's going to shatter into, it's going to destroy. In the second case, because of the spongy materials taking the impact, it takes less time to come to a complete stop, and maybe, the object will not be destroyed, will be quite safe, right? So the impact it feels is much, much less, right? So we're saying that so basically what we're saying is the force in the first case is much larger than the force felt in the second case because of the suspension. Basically, this is suspension, some sort of suspension type of material, springs or soft material, sponges or whatever it is, right? That reduces the impact of the object as it hits the ground or comes to a complete stop. Now, this sort of application, this understanding of impulse is incorporated into designing of cars and planes and things like that, where in the case of an accident, they try to prolong that time for the person inside for example, inside the car, if they have an accident, it prolongs the time for that person to come to a complete stop. So the force that that person will feel will be much less. So we can, if we understand what impulse is, then we can do calculations quite easily. So the main thing is that impulse is force times change in time, right? And when this time is increased, right? In the case for the object to come to a complete stop, when the time is increased, right? Then the impulse will be the same, but the force is going to be much less. Okay. So, but if the change in time is less, then the force that's going to be felt by the object is going to be much greater. So let's have a look at this example here. We'll have a look at some more examples also to illustrate. Right. So right, in this case, we have a car traveling at 50 kilometers per hour. It collides into the car collides into a concrete wall. Right, this is a concrete wall. Right, so you can imagine what will happen when it collides into the concrete wall. There's going to be a lot of damage to the car. Right, so the front crumple zone of the car folds, allowing the car to come to a complete halt over a distance of 50 meters. So it comes to a complete halt over a distance of 50 centimeters. Right, sorry. So as it hits the wall, the car will crumple. Right. So over a distance of 50 centimeters, the crumple zone takes 50 centimeters for the car to come to a complete halt. The driver is wearing a properly fitted seatbelt, but the front seat passenger is unrestrained. The head of the front seat passenger strikes the dashboard and stops over a distance of 2.5 centimeters. Right, so both drivers, they have a mass of 70 kilogram. So first of all, it says calculate the impulse of the driver. Right, so the impulse of the driver, remember that impulse, we start with this, impulse equals change in momentum. So the change in momentum is Pf minus Pi. Right, we'll bring the calculation down here. Copy that. Copy the whole thing. All this information down. Right, so change in momentum is equal to final momentum minus initial momentum. Remember, momentum, P, is equal to mass times velocity. So it's initially the car traveling, traveling at 14 meters per second. So its initial momentum, Pi, is equal to, in this case, we're looking just at the driver, not at the car. So both the car and the driver traveling at the same speed initially. So 70 times 14 meters per second. Right, get a calculator out. Get a calculator anyway. So it's 70 times 14. That's 980. So it's 980 newtons, kilograms meters per second. Right. Then the final momentum. So it says what the impulse of the driver. The driver also comes to a complete stop too. So the final velocity is 0. So 70 times 0 gives you 0. So change in momentum, impulse equals change in momentum, which is PF minus PI. In this case, it is 980 minus 0 is 980 kilograms meters second per second. Right. So the second part of the question, the impulse on the front seat passenger. Right. The impulse of the front seat passenger is exactly the same. Right, because he is also initially traveling. Right. So this is for question I. Question 2, the passenger was also traveling at the same speed and also came to a complete stop, and so impulse is equal to change in momentum, so his impulse is the same. Right, but the force, we said before, right, in the case of the driver, the impulse of the driver, because he has the seat belt on, right, takes less time, it takes more time for him to come to a complete stop than the passenger. So the force experienced by the passenger is going to be a lot more. So here, the third part of the question, the average acceleration of the driver during the car's impact with the concrete wall. So it says the driver, the front comfort zone of the car folds, allowing the car to come to complete halt over 50 centimeters. Alright, the driver is wearing about says the restrained driver comes to rest over the same time and distance as the whole car. Alright. So the time taken for the driver to stop is the same time as the car takes to stop. So it's 50 centimeters. It comes to a complete stop over 50 centimeters, which is 0.5 meters. So in this case, we have to use one of the equations in motions of x equals 0.5. We don't know the acceleration, that's what we're trying to work out. Right, acceleration, the initial velocity u is equal to 14. Right, the final velocity is equal to 0. So we use one of the equations of motion. So we got v equals u plus at. Right, v is equal to 0, u is equal to 14. A we don't know. Actually, we don't know time, so we can't use that one. Can't use that equation. Right, so we have to use v squared equals u squared plus 2ax. So we transpose v squared minus u squared over 2x gives us a. A is equal to v squared is 0, u squared is 14 squared over 2 times 0.5. I'll put in the calculator. So it's 14 squared divided by 2 times 5 196 meters per second squared. Right. Express your answers to question 3. So the average acceleration of the passenger's head during its impact with the dashboard. So the second one is the passenger. The fourth question. Okay, in this case, the x. In this case, the distance taken is 2.5 centimeters, the same as 0.025 meters. Okay, initial velocity is equal to 14. Final velocity is equal to 0. Find out what xa is equal to. So in the same case, it's negative 14 squared. I've got to put a negative there. Over 2 times 0.025. You can see it's going to be much more. So that's again 14 squared over 2 times 0.025 and enter. 3920. 3920 meters per second squared. It's quite large. Right, express your answers to questions 3 and 4 in number of g's to which each person is subjected. The number of g's is multiplied as a multiple of the magnitude of acceleration due to gravity. So imagine it's gravity. Gravity is equal to 10 second squared. So we divide each one by 10. In this case, it's going to be 19.6 Gs. In this case, it's going to be 392 Gs. Right, so it's much larger. Right, but quite devastating impact. Right, okay, B. I've done that one. C. Someone can see down. Write a paragraph explaining how seatbelts reduce likelihood of death or serious injury. Right, so here it doesn't actually ask us to calculate the force, right? But if we were to calculate the force, we could do it because it takes a lot less time for the passenger to come to a complete halt, and we can imagine the force on the passenger is going to be much larger, right? So that sort of explains briefly what impulse is all about. To understand a bit more further, to understand it further, we'll have a look at some more examples, which I'll show in the next video.